All right, folks, so we are on chapter 3, and it is stoichiometry. So when we think of stoichiometry, we need to think about reactions, balancing reactions. We're going to be using molar mass and the periodic table to determine masses of formulas, and we'll do coefficients for mole to mole ratios. So let's start with what you need to be able to do in this chapter. One of the things you want to be able to do is you want to be able to calculate formula mass. And sometimes this is also called molecular mass. And molecular mass is if you have a nonmetal with a nonmetal. You also want to do percent composition of certain compounds. So like you might have a percent of hydrogen in the sample of water, and that is by mass. So we're going to be using the periodic table. You'll need a periodic table for this one, for all of them, okay? So you'll need a periodic table for these. The other thing you'll want to be able to do is we'll need to balance chemical reactions. So we'll do some problems on balancing reactions. And we'll use we'll use molar mass in reactions because we want to. So you'll calculate molar mass, which is pretty much the same thing as calculating formula mass, but you'll use molar mass in reactions and also the balanced reactions to calculate quantity, maybe like grams of starting materials or moles, and we'll also, or product. So that's the whole stoichiometry, and you'll introduce mole and Avogadro's number here, and then we will do percent yield for reactions, and we will skip section, so you can go ahead and skip section 3.5. I can just tell you what it is, and then there are the checkpoint problems with 3.5, and at the end of the chapter in that section that you can skip those. I'm not going to have those on your exam. And then we'll finish up, like I said, we'll do also limiting reagents. So we've got a lot. So this might be long, so do not watch this all at one time. All right, so the first thing you need to be able to do is calculate molecular and formula masses. So you have here, what is the molecular mass for citric acid? And it's H3C6H5O7. So it's asking for molar mass, molecular mass. So what is that? And this is your checkpoint 3.1.1. Okay, well, first thing you see these subscripts, they tell you how many elements there are. So you have 3 hydrogen, you have 6 carbon, you have 5 hydrogen, and 7 oxygen. I'm going to double check this. So that's the same thing as having 5, 6, 7, 8 hydrogen. So we'll just put a mark through there. And then you want to look at the periodic table, and you want to use the number that has 2 digits to the right of the decimal. And that's your average atomic mass. So when you look at hydrogen, I do that all the way out. And these are grams. I do grams per mole. And rather than atomic mass unit, they are interchangeable. So you're going to take 8 times that. This one you're going to do 6 times the carbon is 12.01 grams per mole. And then oxygen is 7 times 16 grams per mole. And then when you total those up, and I take the time to write them all down so I don't make a silly mistake. This is 8.064, 12.01 times 6, 72.06, and then 7 times 16 is 112. And then you can add these all up. It's also good to do this too because the next thing you have to do is percent composition. And so if you already go ahead and you have the masses from like hydrogen or from carbon or from oxygen, then you can quickly figure out the next step. Okay, so let's add this up. 8.064 plus 72 plus 0.06 plus 112. So I get 192.124 grams per mole, and I take this out to about 2 to the right of the decimal, and I look and I see 192.12 atomic mass unit. Answer is A. And that's how you work that problem. And you should be able to do the next one. So I will just do one example for each of these for time. Okay, the next thing you need to be able to do is percent composition of compounds. And so what is the percent? So we'll do the second one, 3.2.2. Percent composition by mass of sodium bicarbonate. So the first thing you want to do, step 1, is calculate, and this would be the formula mass. And it's called formula because it's an ionic compound. So we have 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens. And then I look at my periodic table and I see that sodium is 22.989, so that's 23.00 grams per mole. I see hydrogen is 1.08 grams per mole. Carbon is 12.01 grams per mole. And oxygen is 3 times 16 grams per mole. And then I add these up. And so these are 1 times 23, 1 times 008, 1 times 12, and then 3 times 16 is 48 grams per mole. And then I add that up, so 48 plus 12.01 plus 1.008 plus 23, and I get 84.018 grams per mole. So that's the formula mass for this compound. Now that's the bigger number because that's all of these elements. Okay, so this is going to be on the bottom. So when we want percent composition, we want the part, so this is the small, over the whole. Okay, and that's going to be the big, and then you multiply by 100%. And so that's how you do percent composition. So if you want sodium, then you take the mass of the sodium. So percent of sodium equals the mass, 23.0 grams per mole, divided by the whole. And the whole is here, 84.018 grams per mole. And then you take that times 100%. So 23, the part of sodium, divided by the whole, 84.018, and that times 100, and you get 27.38%. And then we're going to do the same thing with our next one. So let's do this with hydrogen. It's going to be a small percentage, folks. So percent of hydrogen equals the part of hydrogen, 0.008 grams per mole that belong to hydrogen, divided by the whole, which is 84.018 grams per mole. And you could round this times 100%. So I do 1.008 divided by 84.018 times 100. I told you it would be small. 1.20%. All right, and now we're on carbon. So let's do our carbon. And carbon, the part of carbon is going to be, so percent of carbon is the part's 12.01 gram per mole. And we're going to divide that by the whole, which is 84.018 grams per mole times 100%. So now we do 12.01 divided by 84.018 times 100. So the percent of mass that belongs to carbon is 14.30%. And then our last one is oxygen here. And so the percent that's oxygen would be 48.00 gram per mole divided by the 84.018 gram per mole times 100%. So 48 divided by 84.018 times 100. And that is 57.13%. And then I always check, I add up all these percentages to see if they come close to 100. They should be, and they're exactly. If you add this up, I get 100.01%. So they should all add up. Now I can look and see which one matches. And it looks like E is my answer. And you can check that answer in the back to make sure that it's correct. Okay, the next thing we're going to do, folks, is balancing equations. So we're going to balance equations. And a lot of times this just takes some practice. So let's go straight to the problems, the checkpoint problems. So we have 3.3.1, and we have methane, and we have water. This is a combustion reaction, and we get hydrogen gas and CO2 gas. Now, I liked how your book did the dashes. It's the first time I've seen that. So this is the reactant side, and this is the product side. And so the first thing you want to do is take inventory. So the carbon, so here you have one carbon, and over here you have one carbon. And then you have the number of hydrogens. So here you have 4 plus 2 here. So you have 6 hydrogens, and over here you have 2 hydrogens. And then the oxygen, you have 1 oxygen on the reactant side, and you have 2 oxygens on the product side. And so now you'll want to go through and balance them. So right now the hydrogens are balanced. I mean, the carbons are balanced. The hydrogens are not balanced. So we have 6 here and 2 there. And so you could go in and put a 3 there. And if you did that, 3 times 2, that makes that 6 now. And so they're balanced. And then we've got to go and do the oxygen. So we've got our carbon, and our hydrogen. So if we have 1 here, if we want to put a 2 there, so the coefficients, you put the big numbers in front, that changes our hydrogen now. So we have 4, 5, 6, 7, 8. So now we have 8 hydrogens, but we do have 2 oxygens. So the oxygens are balanced, but now we have our hydrogens are not balanced. So here is 6 hydrogens here. Now what I like to do is I like to go through on these because they can be kind of time consuming. I like to make sure everything's an even number. So what you can do with this is if you want 8 here, make sure that this is even. So if we want to make everything, if we want to multiply everything by 2, so multiply by 2. So you have 2 CH4s. I'll try to keep my same color, plus 4 H2O, and then this would give 2 times 3 is 6 H2 plus 2 CO2. And then I can always reduce the lowest terms, but I like working with even numbers. So if you do this, you have 2 carbons and 2 carbons. You have 8 and 8. You have 16 hydrogens, and you have only 12 hydrogens there. And then here you have 4 oxygens and 4 oxygens. So you still have a problem with your hydrogens. So how can you change this number to get the same number of hydrogens? Can you put an 8 there? And 8 times 2 would give you 16. Okay, so now I just think those whole numbers are easier. And then we want to reduce the lowest term. So let's divide 2 through. And then rewrite it. So then 2 by 2, CH4, 4 divided by 2 is 2 waters, 8 divided by 2 is 4 hydrogen, and then 2 by 2 is 1 CO2. So that is how I quickly balance that. So what the answer for that one would have been 1, 2, 4, 1. 1, 2, 4, 1, and the answer is E. Okay, let's do another one here. Let's do our 3.3.2. So this one's just showing you pictures of nitrogen, and we have 3 nitrogen gas molecules, and we're adding it to 1, 2, 3, 4, 5, 6, 7, 8, 9. These pictures, 9 hydrogen gas, and we're making ammonia, NH3, and we have 1, 2, 3, 4, 5, 6 of those. So those are the concepts here. And is that balanced? So 3, so that's 3 times 2 is because you multiply these. So 3 times 2 is 6, 6 nitrogen, and then over here we have 6 nitrogen. Okay, hydrogen, we have 18 hydrogen, and then you do the 6 times 3, and we have 18 hydrogens. So those are balanced. Okay, let's go to another one. So we're going to do 3.3.3, and we have sulfur, and we have ozone, O3, and we have SO2 gas. And so we do our sulfur first. We have 1 sulfur and 1 sulfur. So 1 sulfur on the reactant side and 1 sulfur on the product side. Then we have 3 oxygens. So we have 3 oxygens on the reactant side and 2 on the product side. And so now we have to put we only add coefficients. Okay, so we only add the coefficients and never touch the subscripts. If you touch the subscripts, then you're changing the actual compound, and that is wrong. Okay, never do that. So we can put in the coefficients, which are the big numbers in front. And so here we have, what's a 3 and a 2? So if I put a 3 in front of here, then you do 3, and this is an imaginary 1 there. Okay, so that is 3. So now we have 3 sulfur, and what's 3 times 2, because you multiply those, 6, so we have 6 oxygen. And if we want 6 oxygen, what do we put in front of here? Put a 2. So 2 times 3 is 6, so over here we can make that 6 oxygen. And then here we have 3 sulfurs, so we can put a big 3 there, and now we have 3 sulfurs. So as you can see, your oxygen's balanced, and so is your sulfur. And that is your balanced equation. Also, you don't want to change, when you're dealing with polyatomics, you want to keep those together. So before we leave balancing equations, let's work one from your additional problems. Okay, so let's do something like 3.24 M. So KOH plus H3PO4, so that's phosphoric acid, and that produces K3PO4, potassium phosphate, and water. Now, you want to keep your polyatomics together when you see something like that. So PO4, 3 minus, keep together. Don't separate those. So let's keep these as one unit. And then first, go for your metals, or the atoms that are not split. So in this case, that would be potassium. And so that's our plan. So let's take inventory. How much, excuse me, potassium do we have? So we have 1 on the reactant side, and we have 3 on the product side. And then our phosphate, PO4, 3 minus, we have 1 on the reactant side and 1 on the product side. We don't have any parentheses there. And then our hydrogens, we have 3 plus the 1, so we have 4 on the reactant side. And I will make the phosphate this one, so we just kind of keep it separated. And then our hydrogen, we have this hydrogen, 1, and there's 3, so there's your 4 hydrogen. And then over here we just have 2. And then we can also do our oxygen. And here we have 1, and over here we have 1. So let's first do the potassium. And so I like to also go for even numbers. So what can I multiply? And I'm only putting in only big numbers in front of the coefficients. So what number can I put in front of here? A 2. So 2 times 3 is 6. So that changes that to 6. And then I can go and put a number 6 in front of here. And I just find time going those big even numbers, and then we can always reduce our terms. Okay, phosphate's the same. Now we got to look at hydrogen. Well, hydrogen changed, right? Because we got 6 hydrogen now. Because 6 times 1 is, so there's 6 hydrogen. And we changed our phosphate too, right? So 2 times, we have 2 phosphates there. So now we're going to have to take care of our phosphates. So what do I put here? If I put a 2 in front of there, now we have 2 phosphates on the reactant side. So phosphate's good. And now we have to do hydrogen. So we have 6, and then we have these 6, because this is 2 times 3 is 6. So 6 plus this 6, we actually have 12 hydrogens. And if you come over here, what number can we put in front of the water to give us 12 hydrogens? It has a 2. So you think 6, so 6 times 2. 6 times 2 is 12, so we can change that to 12. And now we just want to do our oxygens. This 6 with that oxygen makes 6 oxygens because we're not worried about phosphate. We didn't break that up. And here we have 6 times 1 oxygen, so 6. So now it should be balanced. But you see I have large terms here. 6, 2, 2, and 6. So if I divide everything by 2, the lowest term, and then I can rewrite it. So 6 divided by 2 is 3, KOH. 2 divided by 2 is 1, H3PO4. 2 divided by 2 is 1, K3PO4. And then 6 divided by 2 is 3, 3H2O. And you'd want to write that out and highlight that. And you can expect to get an open response question that would require you to rewrite that. You're not allowed to just show your work like this and leave it messy like that. Okay, so practice doing balancing equations. Now we're on section 3.4, and we're doing the mole and the molar mass. And this is where we're going to use Avogadro's number. So if you get your periodic table out, you can see that you don't have to memorize this number. Get used to using it. And you see avo, I think of an avocado. That's what I actually had today. Avogadro. Avocado number is 6.022. So just take it out to that times 10 to the 23rd. And you'll find equals 1 mole. And what is that? It can be atoms. It can be molecules. It could be formula units. So the key here is when you use Avogadro's number is when you see a question asking how many. And when I see how many, I think of Avogadro's number, and this is the conversion factor for dimensional analysis. And that's in 1 mole. And your book talks about like what a mole is. There's also some really interesting like pictures on the internet of the periodic table, and everything's 1 mole, and you see different masses have different moles. So like 1 mole of hydrogen would be 1.008 grams of hydrogen. But if you were to weigh out oxygen, you would see that 1 mole of oxygen is really 16.0 grams of oxygen. And when you actually see the substances and you see the different masses, it's very interesting. All right, so now let's look at the different checkpoint problems. We'll work with 3.4.1. How many molecules, so see, how many, do you think Avogadro's number, how many molecules, we'll highlight this right here, molecules. That's how you know you need to use Avogadro's number, are in 30.1 gram of sulfur dioxide. So that's your given, folks. You always start with the number in the unit. So this is the given. I call that the given, and this is your starting. So you do 30.1 grams of SO2. You put that over 1, and then that's not what you want, so you're going to put gram on bottom. So gram and gram on bottom. And this is where you have to do molar mass. And so you need conversion factors. So let's look at our toolbox. So one of the toolboxes you're going to need, your conversion factor, is Avogadro's number. So 6.022 times 10 to the 23rd, because it asks how many molecules. Molecules equals 1 mole of SO2. And then the other conversion factor that you're going to need is molar mass. And for 1 mole of SO2, you know molar mass, we've done this, okay? So sulfur, so what's the molar mass? We have 1 sulfur and 2 oxygens. So 1 sulfur is 32.066 grams per mole. And then 2 oxygens times 16.00 grams per mole. So let's do the molar mass. So 16 times 2 is 32. And then you add that with the other 32.066 from sulfur, and you get a molar mass of 64.066 grams per mole. And so for 1 mole, the 1 always goes with mole. That equals 64.066 grams per mole. But you don't have to do grams per mole when you're doing your conversion factors. That's gram. Gram equal the mole. Okay, so these are your toolbox conversion factors. So you can see that you can go from gram of SO2 to mole of SO2, and then you can go from mole of SO2 to molecules. So this is our path. So we put grams here because we don't want it, and we can go to mole, 1 mole of SO2. But it doesn't ask for moles, it asks for molecules. And so then we have to put mole on the bottom for 1 mole of SO2. So Avogadro's number, always 1 gets the mole, and also with molar mass, this is molar mass, you get that from the periodic table, always 1 goes with the mole. And so then that's 64.066, but we don't need that, do we? That's over here. At this point, we've gone from gram, so we're at gram here, and then we've gone to mole, so we're at mole here, so we're at mole, and then we can go to molecules. Okay, so now we put molecules on top, and we have to do Avogadro's number, 6.022 times 10 to the 23rd, and then for this one, 64.066 grams of SO2 go there. And so now grams divided by grams of SO2 cancel out. Moles of SO2 and mole of SO2 cancels out. And we're left with molecules, which is what the question asks. So you get your calculator, and you do 30.1 divided by 64.066, and you equal that, and then times 6.022. And I have to do second function EE23 to get my calculator work, and yours might be different. And I get I have 3 significant figures because this is the only measurement. These conversion factors have infinite significant figures. So 3.83 times 10 to the 23rd molecules. And you do want a large number here. You're multiplying Avogadro's number on top, and you would have a lot of molecules in 30.1 grams of sulfur dioxide. Is that a option? 2.83? 2.83. You do have that option, and that option is B. Okay, let's work another one of these. Okay, so 3.4.2. How many moles of hydrogen? So how many mole of hydrogen are in, this is our given, this is where we'll start with, 6.50 grams of ammonia. So you know you start with 6.5 grams of ammonia because it's the only number with a unit. So this is your given, which means this is where you start. And so you put 6.50 gram of NH3 over 1, and you don't want that, so you put gram of ammonia on bottom. Now the question was, how many moles? So how many moles of hydrogen? So this is our question. So now we're going to do our toolbox, and we have to go from gram of ammonia to mole of ammonia, and then we can go from mole of ammonia to mole of hydrogen. So whenever you do gram to mole, this is molar mass, and you find this on the periodic table. And so 1 always goes with the number mole, with the unit mole, and then this you have to look at the periodic table. So we have 1 nitrogen and we have 3 hydrogens. So nitrogen, you get your periodic table, you'll see it's 14.01 gram per mole, and hydrogen is 3 times 1.008 gram per mole. And if you total that up, so 3 times 1.008 equals plus 14.01, you get 17.03 grams of ammonia for 1 mole, and that's your molar mass. Okay, so you can go from grams of ammonia to mole of ammonia, and whenever that's molar mass, 1 will always go with mole, and then that you had to calculate on the periodic table. Now we have to have another one. We don't want mole, so mole of ammonia, it asks for mole of hydrogen. Well, where can we find hydrogen? Can you see that you have hydrogen in that formula? Okay, so you can get another conversion factor, and it's called 3 mole of hydrogen because of the subscript in the formula for 1 mole of ammonia. So that's a conversion factor you can get from that formula with the subscripts. So we can go from mole of ammonia to mole of hydrogen. And it's just hydrogen, folks. So it's not H2. In this case, it would be mole of just hydrogen. And now we know for 1 mole of hydrogen, we have 3 moles of, for 1 mole of ammonia, we have 3 moles of hydrogen. So now we go 6.50 grams divided by 17.03 equals times 3. And I get 1.15 mole of hydrogen. And I need 3 significant figures because it's in my given for 3. Now I'm going to come here and I'm going to look at 3.42 and see if that is an option. I see 1.14. So that's probably a rounding, and I think D is the answer. Once again, you can check those answers in the back of the book. Okay, let's do another. Okay, so the other thing you need to do is figure out empirical formula. So this is a little different. We're going to do empirical formula. That's another thing you need to be able to do. And 3.4.4. Let's do that. So what is the empirical formula of a compound that has 48.6% carbon, 8.2% hydrogen, and 43.2% oxygen? Now, the step 1, when you're doing the empirical formula, assume 100% is 100 grams of material. And so what you do is you change the percent to gram. So that would mean 48.6 grams of carbon that would be 8.2 grams of hydrogen, and it would be 43.2 grams of oxygen. And then step 2, you go from grams of that element to moles of the element, and that is molar mass. And you get that on the periodic table. Periodic table. So that's step 2. So here, 12 let's keep with the same color. So the molar mass here, this is the conversion factor you're going to need, is 12.01 gram of carbon for 1 mole of carbon, 1.08 grams of hydrogen for 1 mole of hydrogen, 16.00 grams of oxygen for 1 mole of oxygen. So that's step 2. And then step 3, after you obtain the mole of each element, divide each mole, number of moles, by the lowest number of moles to provide a whole number subscript. Because when we want empirical formula, we're looking for the subscript for the formula. All right, so let's do it. So the first one, we take 48.6 grams of carbon, and for 12.01 gram of carbon, we have 1 mole of carbon. And so if I take 48.6 divided by 12.01, I get 4.0466 mole. Do not round on this because it'll make a difference. Okay, and then we're going to do the hydrogen. 8.2 grams of hydrogen, 1.08 grams of hydrogen for 1 mole of hydrogen. 8.2 divided by 1.008, we get 8.13492 mole of hydrogen. And then we have oxygen, 43.2 gram of oxygen. And for 16.0 gram of oxygen, we have 1 mole of oxygen. So 43.2 divided by 16, we get 27. Oh, sorry, 2.7. 2.7. So we get 2.7 mole of oxygen. So now we're at step 3, and we want to divide each number of mole by the lowest number of moles to provide whole number subscript. So we have 8, we have 4, and we have 2. So we agree that this is your lowest number. Okay, so if it's your lowest number, if that's your lowest number, then you divide each one by 2.7. So 2.7 divided by 2.7 equals, you can just divide that by mole. 2.7 moles is 1, and it gives you unitless. Divide this by 2.7 mole, and divide this by 2.7 mole. And so when you do that, 4.0466 divided by 2.7, you get 1.5. Okay, this one, 8.13492 divided by 2.7, you get 3.0. And this 2.7 divided by 2.7 is 1. Now, have you ever seen an element with a decimal for its subscript? You shouldn't. It's not right. Okay, so we need to have whole numbers. So what we're going to do, is there a number we can multiply 1.5 to make it a whole number? Because we need whole number subscripts for our empirical formula. So 1.5 times 2 is 3. So we have 3 mole of carbon in our formula. Okay. Then we have to do that to every one of them. So 3.0 times 2 is 6 mole of hydrogen in our formula. And then oxygen, we have 1. So 1 times 3 is 3 mole of oxygen. And then so our formula would be C subscript 3, hydrogen subscript 6, and oxygen subscript 3. And so when I look at that empirical formula, I see C3H6O3, and the problem with that is those are large terms, so you need to divide the terms down for the empirical formula. So divide by 3, CH2O. So do we have CH2O? What have I done wrong? So oh, so this is what I did. Sorry, folks. Okay. It's okay. So wait a minute. Do you see what I did here? I multiplied this by 3. See how it should have been 2? So times 2 is 2 mole. So now let's try our formula. C3H6O2. And that is E. So check that and see if I'm right on that. All right. So combustion analysis, we're not going to do those problems. So you can, for our exams, you can omit section 3.5, the combustion analysis problems. And then if we keep going, we get to section 3.6. And 3.6, we're using calculations with balanced chemical equations. We're also doing limiting reagents and reaction yield, percent yield. So those are the last ones we need to wrap up with. So I'll work a few of these problems. Okay, so 3.6.1, how many moles of lithium hydroxide will be produced if 0.550 mole of lithium reacts in the following. And so you always start with a balanced equation. So even if I'm giving one, I check it, okay? Because, and if someone asks me to work a problem before I spend hours doing it, or minutes can feel like hours, I check to make sure that reaction's balanced. Because if it's not balanced, it doesn't work out, and it won't be correct. Okay, so they give you the balanced equation here. And so let's look, let's make sure we have 2 lithiums, and we have 2 lithiums on the product side. We have 4 hydrogens. We have 2 plus 2, so we have 4 hydrogens. And then we have 2 oxygens, and we have 2 oxygens. So yes, we have a balanced equation. And I just go through, when I do these, I go from that element to that element to that element. And so I just go left to right on the reactant side. Okay, so now the given is the number in the unit. So we only have one given there. And so there's your given. And that's what you're going to start with, 0.550 mole of lithium. And I would highly recommend that you always put your name of your compound, because you're going to be switching compounds. Okay, the question is wanting to know how many mole of lithium hydroxide. So this is the question, how many mole of lithium hydroxide? And we are here. Okay, this is where we're starting, and we've got to get to mole of lithium hydroxide. And so so when you're converting a mole of one substance to a mole of a different substance, okay, so when you put that equal, then you use the coefficients. So you're going to have to look at the coefficients in the balanced equation. So our toolbox, so those are the conversion factors we need to solve the problem, is mole of where we're at, lithium, equals mole of lithium hydroxide. Now, we use the coefficients. So here we have a 2, so 2 mole of lithium give us 2 mole of lithium hydroxide. So now we can go from 2 mole of lithium to 2 mole of lithium hydroxide. That's the only way we can actually change the name of the substance. And you'll find that that works out to be 0.550 mole of lithium hydroxide. And that answer is A. Okay, let's do the next one, 3.6.2. Determine the stoichiometric amount in grams, so we want in grams, of oxygen necessary to react with 5.71 grams of aluminum according to the following equation. So here's your balanced equation. And you've got to double check, folks, to make sure it's balanced. So we have 4 aluminum and 2 times 2, so we have 4 aluminum. And then let's go to oxygen. 3 times 2, we have 6 oxygen, and then we have 2 times 3, we have 6 oxygen. So yes, it's balanced. And now our starting point, what do they want? Their starting is our given. Do you see the number with the unit? So this is a number with a unit. So this is our given. This is our starting point. So 5.71 gram of aluminum over 1. And then you're going to have a gram of aluminum on bottom. Now the question wants to know how many grams of oxygen. So where is oxygen? That's over here. And how many grams is needed to react? So it wants to change. So in our toolbox, we have to go from aluminum to oxygen, because we're at aluminum, we got to get to oxygen. And the only way we know how to do that is, I think, of a mole-to-mole bridge. Okay, so, and then we have to look at the coefficients in your balanced equation. Okay, so here we have 4 in front of aluminum, so 4 moles of aluminum equal 3 moles of oxygen. And so to go from grams to 1 mole of aluminum, that's molar mass, and the 1 always goes with the mole, and you got to look at the periodic table for that. So I'm going to look at the periodic table, and I'm going to find aluminum. It's in group 3, and I see it's 26.98. 26.98 grams, and that's how I get to moles of aluminum, but that's not what we want. So we're going to go from mole of aluminum to mole of oxygen. That's O2, because it's here is O2. But that's not what we want, so we just copy those letters down. Mole of O2, we want grams of O2. And it asks for grams of O2. Okay, so where do we get these numbers? Yes, we get them by the coefficient. So here we have to put 4 moles of aluminum with 3 moles of oxygen. And then for this one, we have to do the molar mass. And so molar mass, we always look at the periodic table to get those average atomic mass units. 1 always goes with mole. So now we look and we see that oxygen is 16.00, but we need 2 of them. So we're going to multiply by 2, so that's 32.00 grams, because that is our conversion factor that we need. Now you can do 5.71 divided by 26.98 equals times 3 divided by 4 times 32. And that is 5.0793 grams of oxygen. This cancels out, this cancels out, this cancels out. Now we need only 3 significant figures. So we're going to change this to 5.08, because this will round into 7 to 8 grams of oxygen. And now I'm going to look to see, do I see 5.08? And I do. The answer is A. Okay, so you can check your problems there. And so we also have the last checkpoint questions in this chapter, and we're going to be dealing with percent yield and limiting reagents. All right, so let's do 3.7.1. And let's do our balanced equation. Calcium fluoride solid plus sulfuric acid aqueous goes to calcium sulfate solid plus 2 moles of hydrofluoric acid gas. Is that balanced? Well, we have 1 calcium, 1 calcium. We have 2 fluorine, we have 2 fluorine. We have 2 hydrogens, we have 2 hydrogens. We have 1 sulfate and 1 sulfate. So that is balanced. Now it says, what is the mass, so that's in grams, of calcium sulfate? So this is our question. And what's our given? Produced, according to the given equation, when 5 grams of each reagent is combined. So 5.00 grams of calcium fluoride and 5.00 grams of sulfuric acid. So whenever you have 2 givens, 2 amounts in a question, you need to think limiting reagent problem. And when that happens, this is your steps. Step 1, you need to convert the amount of each reactant to the number of moles of the same product. So in this product, we're going to do calcium sulfate because it already is asking that question anyway. Okay, and then step 2. Once you do that, you compare the moles of the product for each reactant. And then the least number of moles is the winner. That is your limiting reagent. You work all problems based on limiting reagent, okay? So step 3, start all problems once you solve the limiting reagent from the limiting reagent. Now limiting reagent, reagents on this side, folks. So reagent, reagent, reagent. It's on the reactant side. All right, so let's convert 5 grams into moles of calcium sulfate. So we have 5.00 grams of calcium fluoride. We put that over 1. We're going to go from grams of calcium fluoride to 1 mole of calcium fluoride. And we're going to look at our coefficients, and we're going to see that 1 mole of calcium fluoride equals 1 mole of calcium sulfate. Where did I get these numbers? This was from the coefficients in the balanced equation. Where do I get this number? Molar mass. I have to look at my periodic table, and I see that chlorine has 19.00, so there's 2 of them, plus my calcium, 40.078, so this is 78.08. So if I take 5 divided by 78.08, I get 0.064, and that's, these cancel out, mole of calcium sulfate. Now I have to do the same thing with the sulfuric acid. I'm just going to do it up here under step 1 because I'm running out of space. So 5.00 gram of sulfuric acid, and for a gram of sulfuric acid, I have 1 mole of sulfuric acid, and then you see the coefficients for 1 mole of sulfuric acid, I have 1 mole of calcium sulfate. And that goes to calcium sulfate. Now I got to figure out my molar mass. So sulfur is, well, oxygen is 16. I have 4 of those. Sulfur is 32.07. And then hydrogen is 2.016. This gives me a 98.09 grams per mole. So 5 divided by 98.09 equals, and that is 0.0510 moles. So now I'm comparing this number that came from sulfuric acid. I'm comparing this number, so this is moles of calcium sulfate, because these canceled out. And I'm comparing this number that came from calcium fluoride. So what's smaller, 0.051 or 0.064? That's right, so this is smaller, so sulfuric acid is my limiting reagent. Now I have to do all problems based on that. So the question was, what's the mass of calcium sulfate produced? Well, I have the grams right here. So now I can do 0.0510 mole of calcium sulfate, and for 1 mole of calcium sulfate, how many grams of calcium sulfate do I get? So I look at my periodic table for molar mass, and I see I have 4 oxygens times 16 is 64, plus 32.07 for sulfur, plus my calcium is 40.08. So that is 130 6.15 grams. So now I do 0.0510 times 136.15, and I get 6.94 grams of calcium sulfate. I only need 3 significant figures because I started off with 5.00 grams in the given. Now I look to C. Do you see that? That is answer C.